selected the batch in the beginning, whether you're familiar with this or all these things. You'll be directly substituting the values, you cannot be deriving every time, right? Let's go ahead with the slide. Can you all hear me? Voice clear, right? The voice is clear. Okay. This is also preventing. Right. Let me join so that I don't keep asking you. Number one, traverse loading, right? We are discussing about the chapters on transverse loading. Transverse means across, like the loading is perpendicular to the cross section, right? It might be in the x direction or y direction, but perpendicular to the cross section. Transverse is perpendicular. Remember this meaning. With that, you may be analyzing it may be a concentrated or distributed loading. You have to make this note. It may be a concentrated or distributed loading. And then due to this loading, there will be internal forces equivalent to, which is called shear force and a couple. And there is a loading, the member will create a shear force, the opposite reaction or a shear force, and then the bending moment in response. That is how the member behaves for the given loading. I repeat, for any transverse loading, the member will respond by producing a shear force across the member, right, or perpendicular to the section, and then the bending moment couple is produced. Okay. With this, you may see that you are having two types of responses. One is the shear force, another one is bending moment. All this vertical direction, vertical direction, there will be the member is expanding in x and y direction, right? All the vertical responses are converted into shear.
Sorry, Miss.
Yeah?
Can you share your slide?
Oh, no, share. Can you see now?
Yes.
Okay. All the vertical forces are. So whenever there is a loading, I'm just explaining what is transverse loading. Whenever there is a vertical loading, it will be converted into, because the member is expanding in x and y direction, right? The cross section is responding, right? For any loading, the cross section is responding. When you talk about the cross section, the response of the cross section in vertical direction will be this one, as a shear force or reaction to the member. And all the horizontal will be changed, right? Due to this vertical loading, all the horizontal response of the member will be changed as a couple, right? And thus you have a tensile or compression, right? When the moment is sagging means it will be like this. So you will have a tension at the bottom, compression at the top. Hogging means concave, like this, upward. So you will have tension at the top, compression inside, right? So these types of responses will be there. You have to find out these responses so that you can design the member to withstand this loading. Okay, right. This is what I explained here. The principal superposition method is used. Principle of superposition method is used. The normal stress due to pure bending may be combined with the normal stress due to axial loading and shear stress due to shear loading to find the complete state of stress. Once you know the shear force and the bending moment acting on it for the given loading and also the support condition, you can find the stress. We can find the superimpose these effects to find out your stress by multiplying, because the loading, if you want to stress from load, it is P over A, right? If you want moment, stress is equal to, sigma is equal to, anybody? You already derive the equation, right? If moment couple is given, you can still find out the shear stress, or the stress, normal stress acting on the member. Sigma is equal to, recall your bending equation. Sigma is equal to my over bending equation. If asked in the exam, I will provide the generic equation. You should know what is what, right? The definition of or meaning or the name used for each notation. I will not give the meaning of each notation. I just state the equation in the formula sheet if asked in the exam. Okay. Now I'm asking shear stress. Normal stress sigma is equal to. Later we go to shear stress. First do the normal stress. Normal stress sigma is equal to, in terms of couple, My over. Forgotten. Don't take much time.
I.
Very good. My over I. This is a famous formula, the equation that we derive. Whenever the couple is given, you can find the normal stress by using this formula, right? This is how we solve by making use of the principle of superposition. Let's do the revision before I go into do the stresses. We done some of the stresses, but now we have to go deeper into finding the stresses using before stresses the bending. We must know in and out of how to find shear force, how to find bending moment, how to find the maximum, where it is zero, where it is maximum, what are the profile, shape of the profile, right? When it is contra, right? What are the contra points of contra? All these things you should know to find the stress as the next step. Right. A small revision on engineering dynamics for finding shear force and bending moment. Every day they are all about the shear force and bending moment, or the every design will have like this. Take this building. If in the building construction, it has beams and columns, right? Any building, any frame structure, any frames will have beams and columns. Beams will be running this direction, 1, 2, 3. Columns 1, 2, 3, 4, like this. Columns and beams are forming your structure, connected by connecting the slabs. Slabs, don't worry now. Let's do the beams and columns in this module. When you due to this loading, start from here. This is a foundation. It's a basement or foundation. This column is supported by this basement, and the entire loading is acting onto this structure, right? Due to this, it will bend like this, and then like this, like this. When if you take the space frame analysis and the result of space frame analysis, the frame structure, you will have these types of bending. Here, if you look into this one, it's sagging and then hogging, sagging, hogging, and then sagging, sagging, a bit of hogging, and then again sagging, hogging, sagging, hogging. Like that, you have a different types due to the number of loading. When it goes here, no, you take this one. When it goes here, it's only this much loading, not many, right? It's already the other end is conveniently supported by all these things, right? So you hardly have this much loading only, so a little bit sagging, not very high. As you go along, you will have different shapes of the bending moment profile and corresponding shear force diagrams. So we are doing this part only. You must know where we are, what we are doing. We are analyzing this structure which has beams and columns. Quickly recall the loads that you will be analyzing. In any beams and column, right? In any beam and column, you will be subjected to dead load, the self height of the member itself. Right? If you say it's a cross section as steel member 20 by 20, then you have the self height of the member itself equal to 20 by 20. Area 20 by 20 times the intensity, right? The density of the material. If you calculate, you will get the weight. So you have dead load, live load, all the moving load, all the objects which is in dynamic position condition, inertia and the forces. In addition to that, it will create its own responses, right? Sometimes it will form as a loading to the other end or to the following members. So you need to calculate, you know this, what is the inertia of the member before you select. And then finally, centrifugal force, loads or forces, just the forces, other types of forces that are acting on it. It may be other type caused by other types, not apart from this dead load and live loads and this type, right? If you talk about the mode of loading, it may be a point load which is concentrated at a point or distributed. It may be distributed or spread over the member to a certain distance. It may be for whole member, a part of the member, or at support from some distance from the support, and so on. So that is called distributed. You should know it. And these types of loading, based on the response of the member, we call this as, it's a kind of a tensile load, compressive load, it's a twisting load. If the member is twisted due to the load, it is called twisting load. Bent, the member bent means bending load. Sheared, only shearing caused by the load, it is called shearing load. So you must know this classification. And you know the units, the bending moment shear force is in Newtons or kilonewton. Bending moment is Newton meter or kilonewton meter. Introduction. Types of beams. You must be knowing types of beams, effects of loading on the beams, the force that causes shearing. Force that causes shearing is known as shearing force, right? 1 over the layers. The layers will shear over. It's not a whole member response, but layer in between the layers they will respond, or there may be a crack at the particular layer only, and it's called shear. Because of the one layer shearing over another. The force that results in bending is known as bending moment. We can draw these diagrams. Loading, it may be shear force, effects may be shear force or bending moment. Altogether, we put the effect, the response of the member to withstand the load, or like this. All the vertical load are converted into shear force, horizontal load are converted into a couple, which is bending moment. By means of these two responses, the member is stable for any type of loading that is coming on the building or the member. Accordingly, how you design as an engineer, want to design for how do you give the response to the overcoming load by designing a shear reinforcement. All the ribs, all the links that are connecting the reinforcement. Later you will study about this shear reinforcement. This is the covering one applied horizontally like rings. I will show later. This is not main concern of this study. But shearing reinforcement will be all the rods are provided horizontally and are bound by the rings at some spacing. Shear reinforcement. And the bending moment by design flexure reinforcement. Whether it's a tension or compression, you will provide the rod at the bottom. If it is the tension at the bottom, if it is both compression and tension, then you have to provide rod at the top and bottom to withstand the loading or keep it in position. All these things are determined by using equations of equilibrium or equilibrium equations, which is sigma f is equal to 0, all forces acting in y x direction equal to 0, all forces acting in y direction equal to 0, and the moments about any support or any point should vanishes. If there is any moment, then there is a failure, there is a bending. Bending should be 0. Keeping this condition, applying this condition, we can find the unknown. Let's see how we are finding out. Principles of moments. Are you following? Any questions so far? Right. The moment of a force indicates the tendency of a body to turn about an axis passing to a specific point O. Moment is always acting about a point or about a section. Mostly it is about a section because it has directions. Better to follow by about a section or a axis, right? And otherwise a point. Always about a point O. Point O. Okay. These are the examples you are seeing here. The principles of moments, which is sometimes referred to as Varignon's theorem, way back in, say, 17th century, about 17th, 18th century, they followed this one. Maybe Greeks and Roman, they are the one pioneer for our civil engineering construction. Rome, Greeks, Athens, buildings. The moment of force about a point is equal to the sum of the moments of the forces, components of the forces about the point. That means it should nullify, the moment should nullify. The resistive moment should be nullifying so that the member is stable for any type of loading that is coming on. That's the meaning of this one. In two-dimensional analysis, if you treat this, all these types of behavior of the members, the operations, then it will be M equal to force into distance. Always the formula is force into perpendicular distance. That is the moment. For example, this one, if you consider, this is the axis, and this is the axis here. The force is applied here. Pipe wrench is used to rotate, right? Rotate means you are applying a couple to rotate, and maybe it is a removal or fixing, any type of operation going on here. It is being rotated, right? The force is acting at a distance from the axis, of a plate. This is the point where you need the job done, right? The focal point, and you are applying the force here. When you apply the force, it will be different. When you apply the force, it will be different. Why? Anybody? Derek? The force is applied here. All of you know that the moment about this point, how much moment you have to apply, how much couple you have to apply, is given by this times the distance from this point, isn't it? The moment to be applied to rotate this fringe is force into this horizontal distance, perpendicular distance about this axis, so that it can rotate or remove or fix. Now, what if this is here? Direct answer me. If the force is applied at this, the hand is here. How much is the moment, and is it higher or lower than the previous one? Direct. Have to apply more force or less force. I mean, moment is more or less. Force can be same. Moment, how much the moment? Is Derek present today? Angzen? Adel Kamal joined already? I ask question like this. The force is applied here, right? What if the force is applied here? Will the moment increase or decrease?
Decrease.
Very good. I think you got the point. And then going here, again, this is the pulley, this is the middle point you are applying, and the wheel, right? To rotate this, he is applying the force here. Again, for this force, to find out the moment, you need to know how much force you are applying times the distance. Make the job done, right? The bolts are fitted or screw in or screw out. Both can be by applying the force in the respective direction, right? Same goes here. This may be an object, maybe rotating object. Then this is the center. To find the moment, you need to know how much force to be applied to rotate and the distance with respect to the axis of rotation. These are all the moments are determined, right? You have to know this point before you go and analyze. You must know these two terms. We are doing until engineering stress analysis. You will be following this one. I am not getting you into indeterminate beam, but in theory of structure, I think theory of also are not having. I think so, because in theory of structure you will do all deflection values, and then frame analysis and so on. When you go to next level, I don't remember what is the subject, but the next level will be analysis of frames. When you go for analysis of frames by applying moment distribution method, stiffness matrix method, you will follow this indeterminate beam. Now all determinate beam. Until stress analysis and design, you will analyze only determinate beams. What is determinate beams? Means this is following the equation. Have to follow all sigma f is equal to 0, all sigma fy is equal to 0, m is equal to 0. If it is complying with this, then your member is said to be determinate beam. That means the number of unknowns is equal to number of equations you have. Okay, if there are two unknowns, you should have two equations to be solved. If you have four unknown, you will left with three equations only, right? If there are four unknown, then it automatically falls into indeterminate beams. These things you will analyze in later, like year 4, year 3 or year 4. Now we have only determinate beam. All will follow or comply with these three equations of equilibrium. Meaning we are analyzing the beam at equilibrium condition. In equilibrium, we will discuss in the next modules, right? So I repeat, if a support prevents translation of a body in a particular direction, then the support exerts a force on the body in that direction. All of you know that you are standing, right? Somebody is pulling, you will pull, you will get displayed, right? Somebody's so suddenly if 100 ton is put on your head, you will sit down, right? You will cramp. So like that, whenever there's a load acting, there's a displacement or there's a translation, there's a deformation taking place, right? The force and moment reactions at supports can be, all these type of force and moments can be, or response of the member can be found out by applying these equations. All the unknowns, the responses, the reactive moments and shear forces can be found by applying these equilibrium equations. Let's see how we are going to do that. For this you have to remember, actually I have to say remember. You need to remember some of the rules, sign convention, and it's all developed for our convenient way of analysis and representation in the design and drawing. When you take to site also, the member, the engineer at site should be able to understand what you have designed, right? That's why we are following one rule, which is shear force upward positive, shear force downward, negative, right? And if it is in this case, it is taken as a member altogether. When you see the member is lifted, right, going up, and here also member is going up. That's why the total is said to be 4. Or in one word, all upward direction forces are positive, downward taken as negative. Keep this in mind. Similarly, moments. Couple supply, if that is causing a sagging, this is sagging. I think the meaning is not written here. Sagging, sagging, sagging. This is hogging, right? How do I let it be? I will correct later. I cannot. Right. And then positive, negative. We can also use the positive, negative. How we are going to do that? All the sagging taken as positive, hogging as negative. Please remember this one. Otherwise, you cannot properly draw the diagram. Remember this convention, sign convention, and then come on. Next is the support conditions. What are the support conditions? Quickly, so go through these things so that we can do some more calculations at the end. Where we are in this case, types of support. Types of supports and reaction and moments will be like this. Based on the support also we can classify the members into different types. Number one is the good old one is simply supported. It has a hinge here, a small hinge, just a hinge, and then here is a pin, just a pin. It is as though a member is kept onto the points there. Simply supported or hinged or pinned. We can call this as simply supported, hinged or pinned. The notation will be like this. Just at one point it is pinned only, not all together, and the whole cross section is not clamped. Only at one point, say for example, if the depth is 20 centimeter, it may be about 20 centimeter means about 5 centimeter or less than that it will be having a screw here or a pin here. And here also it's just kept on it, right? Just kept on it. It's a point or just a bolt or a nut, just kept on it. And then this is called simply supported. Okay, it may be both at a hinged or both end pinned or one end. The good old example is the one if you go to park garden, you can see the benches there, right? The benches are very good example for simply supported. They just kept on it. People can sit and then they just kept on it. Anytime it can break. I mean, if it is see the load, right? And then here is the overhanging beam. Some portion is overhanging at one side, right? One end is pinned like this at this point. The other end is pinned not at the end. If it is at the end, then it is termed as simply supported. Now it is pinned some distance inward, right? Some portion is hanging, overhanging, then the reactions and moments will be different. You need to analyze properly for this case. It is not similar to this case. So some portion is overhanging here, then it is called overhanging beam. No support, no support. It's like a overhanging. Anytime it may deflect, right? And this is cantilever beam. Cantilever beam is one is completely fixed, maybe driven into the wall or welded, right? Riveted with the brackets and so on, firmly into the wall, into the structure, into the frame. Restrained, it is totally restrained. Moment is totally arrested for this member, then it and the other end is free. Then it is called cantilever. This cannot be called as cantilever because this end is just pinned only, right? You may think, well, here also we have free and why not be cantilever? No, cannot. It's a overhanging because it's a pin. If it is fixed here, then it can be treated as cantilever. I repeat, one end is fixed, other end is free means cantilever. When you see the restrainment, it's just a kind of a roller. You can call this also a roller or just a pin. Meaning what? Okay, I go to the next slide, then it is very clear. I will come back again for this slide after showing the next one. Members with support loadings applied perpendicular to their longitudinal axis or core beams. So always it is loaded perpendicular to the longitudinal axis. If this is a longitudinal axis, loading is on top. If this is a longitudinal axis, loading is on top. Always perpendicular to the longitudinal axis. Then it is called beam. Now, this is an important slide for you to understand the reactions. Take one by one. Example, I go for this condition. Roller support. When you see this condition, right, when you see don't worry about the inclination. It can be on a plane surface or an inclined surface, doesn't matter. Let's see one by one. Roller on this plane, right? It is acting like this. When it is all about whether the moment is restrained or not. Okay, depending on that, you will have corresponding reactions on the moments. Read here. As a general rule, if a support prevents translation of a body in a given direction, right? When the moment or the translation is prevented in any one direction, then a force is developed onto the body in the opposite direction, equal and opposite, to balance out. The member will try to provide equal and opposite force to the restrainment, to the force acting on it. Similarly, if rotation is prevented, a coupled moment is exerted on the body. So in both ways, it may be a force or a moment. In both cases, member will respond in the same direction, opposite and equal quantity, equal magnitude. So following this, if you see here roller can move like this, right? But moment about this direction is prevented. Moment about this direction is prevented. Hence the member is showing a equal and opposite reactive force for a roller support. Moment is not restrained, it can move because it's roller. Maybe a trolley, crane, trolley, a train, all are good examples. It can move only in this direction. Moment about this direction is prevented if you take in a plane. So the member will show a reactive force or develop a force in an opposite direction, right? In opposite direction, where the translation is prevented. There is no translation in this direction, so it will provide an opposite reactive force in this direction to support the member. And then when you come here, in this cable, imagine this cable is pinned at this point. Okay, again, don't worry about the inclination because it follows the direction of force. Later, when you want to go for actual analysis, you have to resolve into respective directions to solve. For now, see this diagram, cable, a pin at this point, right? A pin at this point. Similarly, it can move in this direction, right? It can move in this direction, but not in this direction, right? If you consider to be a plane, it can move like this because of the pin. It can move in this direction, to and fro, but cannot move in this direction. That's why it is applying a reactive force in this direction, equal and opposite, which is F. When you come here also, whether it's up or downward, it depends on the magnitude and the support. Okay, don't worry about the value, the sign, but it will exert in the direction where it is restrained. So this type of moment is restrained, that's why it's reacting in this direction. And then when you come to fixed support, completely arrested. Completely, cannot move this way, cannot move this way, cannot move this way, cannot move this way. If it is inclined also, cannot move this way, cannot move this way. So it is completely arrested. Movement or translation of the member, right? The reactive force is very effective because it is restrained in this direction as well as in this direction. Because the moment in this direction is restrained, it will provide a reactive force in this direction. And then because the moment in this direction is prevented, right, to and fro prevented, it will react in such a way that by providing a reactive force developed in y direction. Both, here are both. In addition to that, and moment, I already told you, for any loading, any restrainment, any type of reactions will be shown by member in two ways. All the vertical forces in terms of shear force, all the horizontal forces in terms of, if there is any stresses developed inside, it is converted into moment. By means of moment or bending, it will show the response. If there is a proper reinforcement, this will not occur, right? Knowing that there is a failure of this amount, engineers will provide the reinforcement to support this couple developed due to this restrainment or other type of loading on it. And then incline, right? The resultant will be acting. Then thus you will have, for this type of loading, it will be a resultant force and then a couple. This is a final result of this fixed support. And then coming here, again it is pinned. Pin means it can move in this direction. It cannot move because it's inclined, right? Why I have two forces? Because it's inclined, right, at an angle. So I take this one. So the pin, you can move like this. You can move like this, right? Above the pin, you can move like this, but cannot move like this. That's why it is restrained, right? I can even put the arrow here. It is because the moment is restrained in moving in this direction. It will develop a force in this direction, and then it is in two components, because it's inclined, the member is inclined. You will have two components, which is x and y. If it is a horizontal member pin, you will have only one, either y or x, like the usual questions and answer you're doing for calculation of shear force and bending moment. I repeat, because it's pinned here, there is a restrainment in moving in this direction. The member will impart a reactive force in this direction, and this is not a one, it is in two form due to inclination at an angle, right? The member is not horizontal or member is not vertical, it is fixed at an angle. Hence the response will have two components, namely vertical and horizontal, like this, and the resultant is shown here. Okay, any question you can ask me? You need to think. When I say you need to think, then only you can conceive the meaning, you can be firm on answering, right? Any question? Are you there? I didn't take attendance. Any question? Please talk. I don't know why you are not talking. Two people. Adil Kamal is missing. What happened to him?
No question, miss.
Any other? Okay.
No, teacher.
Okay. Any question, you can disturb me anytime. I go again. Please see whether the slide is shared. Slide is there, right? Okay. If not, you tell me. Okay, let's move on to this one. You have to, in this slide you need some remembrance. I'm sure you'll be solving at least 25 to 50 marks in your exams. Part of the question will be like this. That's why I'm insisting more on this type of calculations. This is the basic for your analysis. Load, shear, moment. Let's understand the shape and the profile and how it is. Number one, whenever this is a horizontal member, hinged, right, or pin or roller anytime, and there is a moment. When there is a moment acting on it, the moment diagram will be, it will be a sagging, right, nearly a sagging, because it tend to move. Translation is not arrested, right, it can move. A moment is zero, just like this, it will bend like this, sagging, positive, so you have positive value. And then like this, when you come here, it will be hogging. When it move like this, hogging, negative. What are you, I've got a shear force, right, somewhere here. Oh God, shear force, we are talking about the shear force. When you convert this moment into shear force, right, there is some value here, reaction due to this moment, and there is some reaction here. That's why you have the values like this. And then when you come to loading like this type, there is a load, right, and there is a reaction. When 20 is acting, there will be a 20 opposite direction, then only it is balanced. Altogether, you will have a positive value like this. And then this one, constant UDL, right, constant UDL. I already told you shear force in a point, if it is a point load, it's a horizontal straight lines. You have to remember this point. If shear force UDL, it will be an inclined line, meaning the distribution is start from here. There is, because it's a UDL, it will have a reaction at this point. You have some value here, and then gradually increasing, right? Gradually increase. It should be cantilever. Oh yeah, fix here. See, fix here. Cannot be like this. It's a fix end, but UDL acting. Cantilever, UDL acting on it. Because it's fixed, there is a reaction. That's why you're plotting some value here. And then moving on, that is a loading, right? There is a loading and response. Why it is tending to incline in decreasing? Because there is no other support or reaction here. So naturally it will gradually reduce to 0 at this point at free end, because it's free end. In these cases you have some loading, in this case you have some reaction, in this case it's free. That's why it is going on reducing. There is some UDL here, some UDL go to 0, no UDL at all. That's why it is reducing to 0. You have an inclined line. Moment, coming to moment, because of this reaction, when you go here, this load into distance, there is some load, right? So from here 0, starting is 0 always, right? Because force into distance is 0 here. So start from 0, gradually increasing because there is a moment acting. Load times distance, there is some moment. Moment is a conversion of, combination of force and distance. Because of this moment, slowly increasing to the maximum at this point because there is a moment, right? And also a reaction. First is a reaction. From here to here is a response of the reaction. From here until left side of this point is a reaction, due to reaction. Reaction into distance, reaction into distance until left side of this point. When it comes here, there is another moment added, which is this moment. That's why the value goes down, the moment added. And then further, it's all due to the reaction and the distance, right? Goes down to 0 here. At this point there is no moment or distance available, so it turns to 0. This is how moment distribution diagram for a condition of this support, hinge support, says hinge or roller support at the ends with a couple acting or moment force acting at the middle. You see here the maximum, okay, it's better I show with other diagram. This one constant. Coming to constant point load, start here moment, there is a reaction, right? There is a reaction. There is a reaction, and another thing, reaction not causing the moment here, because it's fixed n, note this point, underline this word, because it's fixed n, there will be a fixed n moment. When you go to higher level, like year 4, year 3, I think theory of structures and what do you call, I forgot the module name, it's a design or analysis paper, you have a higher level analysis or frame analysis will have all fixed n. So you will have fixed n moments and the formulas are there. Either you will derive or you have to remember those formula to apply. Whenever there is a fixed n, it will impart a moment, reactive moment, because it's fixed. Free, no moment, 0. It can move freely. Because it's fixed, no moment, moment is arrested, the member will react to this arrestment for any loading. Okay, when you come here, because of the fixed end moment, you have some value here. But after this is no loading here, but there is a loading and gradually increasing. When the moment after this is, it's all due to gradual decrease, right? It is slowly away from the support, right? It is slowly away from the support. So the value of the moment is reducing until reaching 0 at the end. There is no distance or force acting on it, load acting, but there is no distance, so 0. That's how the moment distribution diagram for a cantilever with a point load will be. And then UDL, start from here. Again, because fixed end, you will have fixed end moment, the reaction, not reaction, the resistive moment will be there. Thus, you have some value which is sagging, hogging type. Both cantilever is hogging type. That's why it's negative at the bottom. Hogging, start from here. You can follow anyone, positive or negative. It depends on your convention. So start from here, some value, maximum value, and then it is slowly reducing, right? Because it's a little bit away, right? It will be a little bit away, but there is some loading, right? There is some loading. You see the curve, this is a straight line, but this is a parabolic. Always moment distribution diagram is parabolic for a UDL. Okay, it's not an inclined line, parabolic, because the distribution, the response is slowly, gradually reducing. It is straight reducing at some rate, constant rate, but it is gradually, right? Exponential or we don't know what is a parabola. It is exponential or logarithmic or what type of parabola it is. So it will be in the profile it is gradually decreasing in this way, in this shape, reaching 0 at this end. And then coming to this diagram, load, point load. This is all about loading and moments. Again, point load at this point, same similar explanation. When it is acting at this point, there is a reaction. No moments at the end for this type of simply supported, but there will be, because it is not restrained, right? There is nothing to react for the member. It can freely move. That's why moments are zero at the ends. Due to this loading, there will be a reaction only to balance this load. That's why you have some load reaction going to top positive, keep on increasing. At this point there is another load added, so it will reach here. Maintain the same until it reaches this one, because there is another reactive force. It cannot stop here. There is another reactive force at this end, so it will drop down to 0. Corresponding moment will be, start from here, moment is 0 here because simply supported can move freely. 0 moment, no resistive moment offered by the material. Keep on increasing because as you go inside, the distance is increasing and the load is also there. So there will be a, because of this loading, there will be a gradual increase in moment due to distance, and then reaching a maximum at the middle, then going down, gradually decreasing to 0 at the end, because totally away from the there is no distance at this point. There is some distance, some distance, some distance. That's why you have moments here. At this point, no distance, 0. And then here, constant UDL. I already told you, similar to this one, we can have the explanation for shear force and bending moment. Repeat, there is a reaction. Due to reaction, you have some value. And then loading, right? Loading is a gradual. It is not a point load. It is a gradual loading. Because UDL, you must have an inclined line. It is a reaction is more marked here, some reaction value, and then slowly decreasing because it is away from the support. It is slowly decreasing, right? And this is also UDL, right? I'm sorry, distributed load. Every meter only it is increasing. The load is increasing. It cannot have a constant value like this. It is a varying one. Distributed one, right? Distributed one. So it will be slowly decreasing. The force is slowly decreasing because it's balanced out. This reaction is balanced by this load. Okay, there is some load here, some load here, some load here. That's why it started decreasing. Okay, started decreasing. Here there is nothing to balance out for this reaction. There is nothing. But here this load, this reaction is balanced by this downward. The balancing is slowly decreasing because it's totally away. Balance is totally decreasing to 0, and then it is increasing in this direction because it's towards another support. So slowly increasing because it's reaching a reaction. Upward and downward is nearing, and then when it reaches here, there is another reaction, big reaction provided by the member. Then it drops to here, this value. That's how the shear force diagram is drawn. Coming to bending moment, I repeat, UDL is parabolic, right? Not an inclined line like point load, parabolic shape. Start from here, free and 0, no distance, free and 0, and then slowly increasing because of the loading. Loading to distance is there, very high distance, big one, and then on the other direction, it's slowly reducing to 0 at the other end. Okay, because the moment is 0 at this point. So it's a parabolic. Maximum occurs at the middle. Okay, maximum occurs at the middle. You see here, exactly, the maximum bending moment occurs where the shear force is 0, right? The maximum bending moment occurs where the shear force is 0. No loading, so it can free to move. And then parabolic. For this video, this linear type, no need, I don't address too much on this, emphasize too much on this. Triangular load, I am not giving you in this session. Let's understand these two types well versed. And this is similar to this one, only thing you have to go by the area, easy, or integrate from one end to another end. Easy way is integration or by following the triangular formula for triangular. Or okay, you to answer me, how do you find the bending moment using this shear force diagram? Anybody? Any answer? Or take this one. This is very good example. Can we find the bending moment using shear force diagram? Any idea? Anybody? At
Yes.
any point? Oh, good. Tell me the answer.
By
How do you?
using the area.
Very good. Area under the curve will be the value of bending moment because you have force, you have distance. Force into distance can give you the moment. That's why, if not given, don't maybe ask some similar question. Maybe ask in the exam. Maybe. So if you are asked, if you're not given bending moment, I mean you are given the shear force. If you form the shear force diagram, you can quickly find the bending moment or the maximum value of the maximum bending moment or location of the maximum bending moment by making use of this shear force diagram. We'll do those calculations later, but understand these concepts: where it is maximum, where it is minimum. Shear force and bending moment are reverse. Furthermore, any question you can stop me, otherwise I keep going. We have left with another 1 hour, right? Not 1 hour, half an hour only. Oh God. I have the video done already, but let me see whether I have time to play, otherwise I will post for you. Okay. I wanted to post, but I thought I have to give some introduction, otherwise you cannot understand. Okay, these are things you have to remember again. Some remembrance required. Simply supported, like this type, right? It may be a pin and hinge with the load F will be WL by FL by 4 or WL by 4. If it is WL by 4, like this is sagging, point load, that's why it's straight line. The shape of the bending moment diagram will be like this. Just remember, you cannot, for everything you cannot be solving, you cannot be using computer or calculator. Something you have to remember, which is very common for you and familiarized to you, right? Sagging and hogging movements you are seeing here. And this time UDO, parabolic, the distribution is very gradual, not a straight line or a constant rate, like this, parabolic and sagging as well, positive. When it comes to this fixed end, some hogging and some sagging because it's a hinge. There's a hinge. It is not a cantilever. It's a hinge. Because hinge, you have sagging at the end, and then both in fixed. There is a fixed end moment, right? Fixed end moment. That's why you have something hogging, change to sagging, and then hogging. This part you will worry about in your higher classes. When you come here, this is important. Fully hogging, fixed cantilever, one end fixed, one end free, cantilever, fully hogging, like this box, right? Like this box, bending moment. Couple, it's a couple is acting. I mean, there is a couple produced. There is a couple produced. So counteracted, it will act in this direction. With that, your bending moment diagram will be like this, right? And then fixed support with the end load, point load. Here is a couple, is a point load, okay? There is a point load like this straight line, straight inclined lines, because at this time you have a reaction. There is no reaction here, that's why it turned into zero reaction. Or like this, all you can have I already explained similar type of diagrams before. You can have it, okay? This is how you can remember your profiling. Having understood this type of profiling for different types of loading and support conditions, you may have answers like this. This one again you will study in your higher classes. You will be provided with this table. But if the fixed end moments for this certain type of loading like point load, UDL, they will give. The rest you have to derive. Okay, just for your information. No need to remember this thing for now. Right. Summary. At last, the summary before we go for calculation. The summary is like this. Slope of bending moment always determined by the shape of the shear force lines. Okay. Slope of bending moment always determined by the shape of the shear force lines. The slope of the bending moment always determined by the, okay, we take this one. Slope of the bending moment here na, slope of the bending moment diagram always determined by the shape of the shear force diagram. Let's see, I will give some more example later. The changes in slope, sagging or hogging also depends on the changes in the shear force values. Okay, there is a correspondence. In other words, shear force is in proportion to bending moment, but it is not always a direct proportion, sometimes indirect proportion, again depending on sagging or hogging. When shear force is maximum, bending moment will be minimum, vice versa. That's what I show you already in this diagram. Matching diagram. When shear force is maximum, bending moment is 0. When shear force is maximum, when shear force is 0, bending moment is maximum. Shear force is 0, bending moment is maximum. Shear force is 0, bending moment maximum. Vice versa. Then coming here, when shear force intersects its axis, there is a maximum moment. Okay, the intersects axis means 0 1. When shear force is 0, there will be a maximum bending moment. You can follow all these things. When you look, this line gives you the idea of to locate where the maximum bending moment is. You can integrate and differentiate from one end to another end by having an m over x, right? dm over dx from one end to another can find out where the distance is or what is the location of the maximum bending moment. We'll do one calculation like that so that you understand how to calculate maximum bending moment for a given loading and support condition. Shear force and bending moment always start and end with 0 values unless at the point where there is a moment or couple applied. Okay, let's see. Always, most commonly they are end with 0. Most commonly, because there is a loading, there is one. Because there is a reaction, this. Mostly they are ending with 0. Mostly they are ending with 0. End with 0. End with 0. Because it should balance. That's the main criteria. Why they are end with 0? Have to balance. When moment and couple acting, you can take like this: clockwise positive, anti-clockwise negative. It depends on about what axis you are going to determine. Keep the clock there. That is a very good idea, clue for you to find out clockwise or anti-clockwise. Keep the clock in front of you or at the axis where you want to find out about which you want to find out. Then it is convenient for you to know which is clockwise and which is anti-clockwise. Continuous beam for your building, and the first very beginning I show the building. For any building, if you take the continuous beam like first room, second room, third room, fourth room, or it may be a building, room number, house number 1, 2, 3, 4, it is made up of a continuous beam. Their shear force diagram will be like this, like this. I don't want to explain too much on this, I have done already, repeating only. Shear force diagram will vary like this. The corresponding bending moment will also vary like this. You can see in proportion only, right? In proportion, like 0 maximum, 0 some value, 0 maximum, 0 some value, a little bit maximum. Okay, any question you can ask me. These are the things I have done last time for the cantilever beam. Let's proceed with the simply supported. I stop here. Any question you can ask. I'm going to play the video that I already recorded for doing calculation. To save time, I already recorded. Let me play the video now. Any question you can ask me. I take 1 minute to upload display the video for you to go through the calculation. You may have to work along with the calculation, easy for you to understand. I do only single beam and then we do the continuous beam. Any questions so far?
Miss, is this covered in the test too?
Yes. You have 2 more assessment. Thank God you recall my assessment. What about the assignment? The one oral presentation I said. Shall I give the question or you want to take the question yourself? Just quick one. You want to do the question yourself or I give you the question? It's better I give you the question. Is it okay? I give one question each. You please solve. Something similar may come for the exam or your assessment, anything. Practice very well. The question will be somewhat like similar to what we are doing in the class world from chapter 1 to chapter 7. I'm doing chapter 5, 6 and 7 are there. I will try to cover by next week or following week. With that, by 14th week, today is week 12, I'm giving the question today. You have 2 weeks left. Week 14 of Wednesday, you start presenting one by one. You take 10 minutes, not more than that. Okay? If you want to work out, you work out before and then share the screen and then you present it. Better you do the presentation, complete your presentation. This will give you very good confidence. You see, last time when I was working with Nottingham, the student really appreciated. I even called the student to come up on the board and they work out answer. They appreciated that they are given chance to work out on the board. This is how you have to learn. You must sportively come upon and then write the answer, give the answers on the board or explain. Must be outspoken, read more, get confidence in the subject. How you do? By training. Every week, 14 weeks, you are doing the same paper, right? Something similar, right? One week, one another week, they are related. So you must get familiarized as the weeks moving on. And by presentation, I'm sure everyone will get the confidence. That's what I will expect from you. Take it sportively. Either you work out and present to me, or you can share screen and start working out uh, for presentation. Okay, I leave it to you. But I post the question by today. After the class, maybe evening I post, because I have another class and then project meeting. I will give you the question by evening. If not posted by 7 o'clock, please text me. I will post the question with the name. You start working your answers. For the portions that are not completed, you may have to hold on. Don't worry, I will give some time. Right. And now the video. What happened to video? Is here. Nowadays, there become too many classes inside my thing. I have to go by online version for download. I cannot download the video. Give me another 1 minute. Are you clear with the assignment and the test 2 as usual? Week 12, you week 2. Hey, this week, right? Your test, huh? Am I right?
Yes.
Can we have it on week 14? One more additional class. I really cannot finish the syllabus otherwise. Can we have the test on week 14? Is it okay? Everybody agree?
Yes, miss.
Week 14, like Monday. Monday, are you free? Week 14, Monday. Monday, are you free? What time you are free?
Yes.
What time you please choose, then post in the group, post in the chat box. Which time you are free, you post in the chat box. Any objection, others can reply to this message. Any objection for this time? Anyone propose the time for test 2 on week 14? I will do a mark at the same day. It will be quick. Don't worry. Monday is preferable for me. For now, I think I am free now on that day.
Teacher, our exam is on 26th, right? 26th March.
I fix on March 26, but I have not completed my syllabus. I'm worried I need classes. That's why I cannot conduct test on this week 14. I mean, the week 12, the 26 is not test. I want to postpone this.
Okay.
Even if,
Miss, postpone until when? 5th of April.
well, yes, correct. 5th of April.
5th of April, I cannot.
Cannot. What's the problem? Any other test? Any other test?
I need to go back UCSI.
Oh, what do you mean? Go back also, you can do it, right? Oh, you have planning arrangement there. Okay.
Yeah.
Now, 29, is it okay? 29, Monday 29?
We have fluid mechanics.
Saturday 27?
We have civil lab
Love to.
test.
Busy people. 3rd April? Also civil lab.
For 3 of April?
Otherwise, better I suppose than answering, right? I don't have to be there. I mean, I am there.
Oil
But
mechanics is on 1st April. So 29 is free, I guess.
29 is what?
29 is Monday. probably.
Okay.
I don't think we have exams on 29.
29 soil mechanics is on 1st April, right?
Yeah, April is soil mechanics.
So
You are
there's
talking about
nothing on
final.
29.
You are talking about final exam? No, right?
No,
No,
teacher,
ma'am.
it's true.
What?
Mids.
I already seen the timetable. I had a doubt. Okay, confirm me. Maybe you can discuss later and confirm me. Any day I can conduct 2 hours test, 1.5 hours, right? We can do it even the early morning, late evening also okay for me, but not disturbing the regular class. We have to conduct some other time. I need one more class at least. 2 more needed, but let me see. Wait, I take the video
Miss,
first.
what about the assignment? When it will
What?
for for the assignment?
Hmm.
Huh?
Assignment is presentation on exactly on week 14 Wednesday like this. In the class you present it. Okay? You have to
Okay.
present in the class. That is confirmed. That is mandatory to conduct during class hour. But test I can have it on any day, 1.5 hours from today, and I mean like 26 I fixed, 27 onwards any day we can conduct. You decide and post it. Otherwise, let me decide, but not on day after tomorrow. Okay? Is that okay, everybody? Take some time, like study, and then we can have it later. Agreed, right? Okay, let me play the video. Going to be another 20 minutes only. If any objection, anything, you can put in the chat box. Let me go through later. Let me share this screen for you. The calculation part, very simple one. You have to do the voice sharing, include sound. Okay, this part. All of you listen to this video. The tutorial portion. Hi. Good morning, students. Let's continue with the calculations for finding shear force and bending moment and the plotting of respective diagrams without scale. So the sketches, right? So the diagrams you have to do without sketches for better understanding of the analysis behind getting shear forces and bending moment due to the given loading and the support condition. Last class we did for most of the cantilever conditions, right? 3 questions are solved. Let me continue with simply supported. Our second case, and the example is number 4. I take this beam with the hinge support at A, another one roller at B, right? It can be another hinge or roller, you can take it to be hinge or roller, and then the distance is L by 2, L by 2. Okay, right. Loading conditions given, let's solve for this. I want to take a generic one so that you can solve for any type of calculations later on, right? Let's solve by applying. Start with the solution starts with always solution start with drawing given data or drawing the free body diagram. Okay, free body diagram. When you draw the free body diagram based on the theory, I assume that you are thorough of the theory. Just now we discussed in the class about the basis and the background of different types of supports, different types of loading, and the responses, the member due to its member property, right? Apply all this knowledge to solve this problem. Okay. For this type of hinge support at both ends, right? We can have conditions like this. The body diagram will be like this. It will have, due to hinge support, it is free, it is restrained from these two. That's why there will be a reaction due to horizontal and vertical, right? But this is only vertical loading, so you don't need to talk about horizontal right now, just leave it like that. Because of the vertical downward load, I will have the reaction. If I take this as A, this as B, I will have reaction at this point, which is AY. at support A, direction of Y. And then also here, because it's again a hinge support, I will have a reaction at support B in the direction of Y. And then distances are L by 2, remain same. Just mark here for our free body diagram. The load is, free body diagram is the diagram with the load reactions and the distances, right? All the given information. P kilometer, right? Let's move on. The solution is like this: by applying equilibrium equation, right? By applying equilibrium equations. There are three equilibrium equations. Sigma force in x direction is equal to 0. Force in all the summation of forces and summation of forces. First, the member should be in equilibrium condition, right? Member should be in equilibrium condition. If it is stable, stable. Moving, must be moving. Cutting, doing the job, right? It should be stable and at equilibrium condition of doing its job. The purpose may be for weighing, purpose may be for pulling, lifting, mixing, and all conditions or components and the structural member must be behaving without any failure. Okay. So to do this one, I take all bending moment, the bending moment about A or B we can solve. Let's take about A, should be 0. Okay. We can solve by A or B. About A, if you take moment about A, let it be. This is important for moments about what you are taking, right? About what you are taking the moment. Moment doesn't stand alone, it needs a lever on. About a section or a point, you have to take it. Right. Moving on, we apply x direction should be 0 because there is no horizontal force acting on the member. Naturally, there won't be any horizontal reaction provided by the member. So let's go to the sigma Fy. Take this one, sigma Fy is equal to 0. Summation of sigma Fy is 0. Account for all the forces in y direction. Sum all the forces in y direction on this member should be equal to 0. You can start from left to right or right to left. Meaning A to B or B to A. You can go from here to here or you can go from here to here. Have any one direction and then start solving. Let's take from here to here. Let's take from here to here. In this case, all the loading, but I don't put the direction, I'm very confused. It's in the y direction. We are solving for all y direction. Take all y direction forces from A to B. I write down from A to B. Better you write down. Otherwise, you will not know where I'm going. So a sigma Fy from A to B. If you solve, start from A is RAY, and then follow the sign convention, which is positive, upward, and then downward is negative or shear force. Accordingly, I will have this one. RA is positive, and then downward is negative, and then followed by, you have anything else? Yes, you have the last is RBY, which is upward, again positive. RBY should be equal to 0. From here, I can find RAY. My RAY is equal to P minus RAY2, right? So P minus P, I bring the P this side, and then my RAY, okay? RAY. RBY, right? RBY. Okay. Minus, plus or minus, this is minus, it's going to be RBY, right? RBY. Then same, if you solve from here also, you will get the same equation, but in terms of BY. If you want to know AY, you have to know any one, otherwise you cannot solve for the other. Let's find out what is the value of RBY. How much is RBY? To find out RBY, better we must go for another equation. There's two unknowns, must have two equations. This one is also unknown, this one is also unknown. So we need one more equation to solve. Okay, we need two equations to solve two unknowns. So we move on to apply. There is third equilibrium equation. Take moment about A and equate to 0. Let's take the third equilibrium equation so that we can get the unknown. keep it like this equation 1, and then you solve here, taking moment about, taking moment about, taking moment about. My handwriting is clear. Anywhere not clear, please tell me. Taking moment about. I don't have the version in between. I need the thickness in between. Only the thick and thick, the thicker and thick. Distance is the L by 2 at L by 2. And you want to take from A to B, mean A. Imagine the clock is here, the 12, 3, 6, 9. Okay, clockwise anti-clockwise, because moment, right? Better follow clockwise anti-clockwise direction. It is like this, RAB, RBY times the distance will be positive or negative into L. That whole distance is L, right? Whole distance is L. So I will have L, and then this is positive, a negative, right? About here we are taking, it is rotating this direction negative. And then what about the next one? Next loading is this point, right? This P. P into, P is positive or negative? Positive. P into distance is the L by 2 at L by 2 and L by 2. Then anything else acting? After this is nothing. At A you cannot account because at A the distance is 0. So you may not have at A values. You have to account for this only. It's not moving. Okay. Okay. Come on. Have you done all the loading and the distance? Yes, done. Equated to 0. That's all the forces and moments. Now we can find the unknown RBY. Take RBY this side, then you end up left with PL by, end up with P by 2. This is your answer. So you have RBY is equal to P by 2. That's your answer. Right? Let's substitute in this equation, which is P by 2. End up with positive P by 2. So your RAY is equal to P by 2. Very simple, we found out already. Both reactions found out already. We can plot it. Alright, we've got the reactions. We can find the maximum bending moment also. To find the maximum bending moment, we have to go through another type of solution, getting the solution. Right. I do part by part so that it is clear to you. Right. Start from, we got the reactions already. We can mark conveniently here. Can we rewrite the drawing, free body diagram to find the moment? And the second step is to, the first one we found the shear force reactions, and we need to be applying equilibrium forces. You can go from the first type of solution is by getting shear force, okay? Or getting shear force. Or getting shear force diagram. Second one, that I will do bending moment diagram. Okay, we will plot lastly all the diagrams for now, just because I want to compare. Better do it together in one diagram. Let's find the moment, the moment, bending moment. To find the bending moment or maximum bending moment, you have to solve like this. Start with, you can divide into portions like 0 to L by 2 or 0 L by 2 to greater than L. That is also possible. If you want to make it very generic one, let me solve by this way. We already got the reactions. We have to find the moments only. Let me draw the diagram again. You have the reactions already, P by 2 at A, and then P by 2 at B, P by 2 at B, and you have the load P, and these distances are L by 2 already given to you. Now let's find moment. We have to find the moment diagram. So start from this side. You can solve for the bending moment diagram. We have to go from here. At A, you have the bending moment started from A. You have P by 2. Moment about A, about A, and about A. Take moment about A. Then you have solve one by one. As usual, keep the clock at A and do one by one to solve for one. Just keep the clock there. Keep the clock there. You will have it's coming this side. Wait, positive, anti-clockwise. It's total L, and then P by 2 L, and then bending moment at x equal to L by 2. Let's find. Okay, means what at P. So maximum bending moment or max is equal to at this point. At this point, either you can keep the clock here and go from A to B, or B to A. Anywhere is possible. Both our goals should be same because it's equidistant, right? Maximum bending moment will be when you keep the clock here. If you do from A, it will be L by 2 times, right? Reaction P by 2. P by 2 times the distance is L by 2, right? End up with PL by 4. This answer, maximum bending moment. To find the distance at which where it is having the maximum, we will find. We'll do it by proper differentiation. You can find the number. For now, just keep it like this, because it's not most important in our case. And then maximum bending moment is found. What else you need to know? Next case, right? Let's go for the next case. Yeah, I stop here. Example. Fine. Oh no, we need to draw the diagram, isn't it? Let's draw the diagram. Let's draw the diagram for all the member and other things. You have done. Not selecting. You have the diagram. Oh, how much it is? Here, there is another P by 2 here. There is a download, another download. P by 2 is added. So add another P by 2 here. So the line will go here, right? And then it maintains until this point the same value. But when it comes here, there is another, until this is P by 2, there is another P by 2 at this point, so it will get close here at B. So this is how we draw the diagram for shear force. This is positive, this is negative. Okay, negative. Negative. And then this is shear force bending moment diagram. Oh, how much is the value at the end? Because simply supported, the moments are 0. Okay, just now we solved also, we got the 0 value, right? And then maximum occurs at the middle, positive or negative. When this type of loading, you can simply say about the hogging, because one load, right? You can by observation, just nakada, you can say what type of moment it would be, right? For this loading, right? Loading at this point, it will, what is the type of moment? Is a hogging or sagging? It's a type of sagging, which is positive, right? So positive we put downward. You can use the upward or downward number to make it different between shear force and bending moment. This is SFD. This is SFD. This is SFD diagram. This is bending moment diagram. Make it different. I put the positive bending moment at the bottom. The maximum value is PL by 2 here, PL by 4 here, and then this is point loads. It will be a straight line. It will be a straight line. Straight inclined line. Bending moment, also it is an inclined line, and straight line because it is a point load. It means the distribution is like this. The distribution is gradual, and then reaching a peak value, again descending to 0 gradually. So this is called the bending moment diagram, which is positive. Clear? So this one example is solved for simply supported. Similarly, if any calculation, any values are given also, you can solve. Let's say, take this example 5. Example 5 with some value of loading in between, right? Okay, I stop here. Replace the P. Guys, I have to stop here. I will post this video later when you. It was shared or not? Was the video shared before? Can you talk louder?
No, miss.
Why you didn't say? Tell me.
Oh, just now we can see, but you not yet share the whole video.
Yeah, no. Until now you had seen the video, right?
Yes.
Yes.
Okay. I will post this
Yep.
video for completion of other types. I solved few types there. The rest we'll do it next class. I have to join another class. We'll see you by Friday. Okay. I will post the video. Please go through that and keep solving all the rest of the questions. I have given some additional questions for you to do it at home. Okay. Right. See you next class. Bye bye. Any question you can text or message me anytime, right? Or call. You can also call by MS Team. We can clarify through WhatsApp call or voice message or by WhatsApp by MS Team. Okay. Take care. Bye bye.
Thank you.
I have to stop. I have to join the next class.